Hi everyone. The first set of mechanisms that I want to look at in Unit 6 are the hydrolysis mechanisms. And what we're going to discover is that the more reactive carboxylic acid derivatives, the acid chloride and the anhydride, they only require neutral water. But for the more stable ester, we're going to need acid catalysis. And for the very stable amide, we need concentrated HCl and heat. Let me draw those four reactions, and then we'll start drawing the mechanisms for each. Okay, here are the four reactions, and I labeled the four derivatives, acid chloride, anhydride, ester, and amide. And you notice that they all give the same carboxylic acid, because look at the left side of each of these molecules. We are going to cleave between the C double bond oxygen and the leaving group. You might recognize this. This is the reverse of the Fischer esterification. Let us start with the most reactive carboxylic acid derivative, the acid chloride, or some people call it the acyl chloride. And we do have a carbon-oxygen double bond, but we are not protonating the oxygen. This is so reactive that we do not need to activate this carbonyl group for attack. The water is going to attack pretty readily. You attack the carbon of the C double bond oxygen. I'll call it the carbonyl for now. And you kick up the pi bond to the oxygen. Make sure you start your mechanism arrow from a source of electrons. And we don't kick out the chlorine right away. We form what's called the tetrahedral intermediate. Yeah, we do have a molecule that has a plus and a minus. Now, it's important or helpful to remember to go through what's called the tetrahedral intermediate, and that will help prevent you from kicking out the chlorine right away. Right, it's very tempting for the water to come in and kick out the chlorine because that carbon would have 5 bonds. But instead, we go through the tetrahedral intermediate. Right, it started out as trigonal planar. Now we have a choice. Do we bring down this lone pair to kick the chlorine, or do we neutralize the OH2 group down here? Most sources kick out the chlorine in the next step by remaking the trigonal planar C double bond oxygen group. We'll go with regular arrow. Chlorine leaves, it's not going to come back, and we have this. We still have this oxygen with 2 hydrogens, and we did create Cl-, which is conveniently used to deprotonate that oxygen. Let's use a full arrow, and we have our carboxylic acid plus HCl. Here I've drawn the reaction of an anhydride undergoing hydrolysis under neutral conditions. Based on what we see for the acid chloride, can you pause the video and draw out the mechanism for the hydrolysis of this anhydride? Before you get started, I can give you a hint or let you know that it doesn't matter which carbon you attack first with the water molecule. Okay, please pause the video, and when we come back, I'll show you the full mechanism for this anhydride hydrolysis. Okay, when you draw a mechanism, you really should redraw the starter material. I wouldn't draw your first arrows on the structure your professor drew. If we take a look at the acid chloride, it took us 3 steps. We go through the tetrahedral intermediate. Same thing for the anhydride. 3 steps. Go through, there it is, the tetrahedral intermediate. And quite simply, step 2, we kick out the leaving group. Oh yeah, in this case, I never drew that arrow. I attacked this carbon on the right. You could have attacked this carbon on the left. You'd still end up with the same products. There really is not a big difference between which one is more electrophilic. I just went for the one that's closer to the water molecule. Our next hydrolysis is the ester. It is acid catalyzed. It is the reverse of the Fischer esterification. And now that I've seen my products, let me show you where water added for each of these. Literally, we added an OH and an H by splitting this bond, and that's where the water resides. I'm not saying that this is one water molecule, the same water molecule that got split up. It's just that in total, you did add an OH and an H. Same thing here. It just depends how you do the mechanism. What happened here? We added water, so actually in the mechanism that we just drew for the anhydride, I had water attack this side. So I really broke this bond in the mechanism. But either bond is fine. You'll still get the same products. Okay. For the ester, we're adding this water molecule there. There's the reaction. Let me go through this step by step, and then you could do the amide on your own, and we'll still double check that answer. But here, protonate first. Esters are not as reactive as acid chlorides or the anhydrides. You need to convince the water molecule to attack this carbon, because this is less electrophilic, and we're going to convince that water molecule by first protonating the C double bond oxygen. Okay, I shorthand hydronium, H3O plus like this. You could draw the bonds to hydrogen if you need to, or desire to. And we do the protonation. So we protonate before we attack in the more stable ester situation. Do you remember how many steps Fischer esterification was? Well, we're going to remind ourselves because this is the reverse. I don't actually remember, but I feel like I can do the mechanism just by looking at the product of the previous step. What do we need to do next? We did create water, and now that carbonyl group, or that C double bond oxygen, is now even more electrophilic, so we can attack. And since Fischer's all reversible, I'm going to just go ahead and use reversible arrows for every step. We still get, right, the tetrahedral intermediate, but in this case we don't have the O minus, we have an OH. You could probably tell that this is going to be a little bit longer than the first two mechanisms that we saw. Let us neutralize. Right, let's neutralize next. And definitely when you do the mechanism for Fischer esterification, you did go through this intermediate, the neutral tetrahedral intermediate, OH, the alkoxy group, another OH. We did create acid, so I'll draw this one out like this. Okay, we got to kick out one of the leaving groups. We got to kick out the leaving group, right? If you take a look at your overall reaction, we are breaking this bond right here to release the alkoxy. And as long as I'm looking back, here, we get the tetrahedral intermediate after the attack. If you recall the mechanism for Fischer esterification, there is quite a bit of proton transfers. Because this is a group that I want to leave, I'm going to protonate that oxygen. It brings up an interesting point. In real life, what makes this so special? Why can't we protonate or reprotonate these oxygens here? Well, you could, and then we'd go backwards. But for a mechanism, you're looking for the steps that push you forward towards the products. So even though this happens, protonation here to go back, right? It's all reversible. What are they're called the productive steps. What are the productive ways to get closer and closer to the product? Alright, that's just on the side. Let me see what we protonated. We protonated the alkoxy group. I'll draw it like this. We have the OH down here. We did create water, but I don't think we're using it in this step because now we're set up to kick out the leaving group. And we have this, like that. Okay, what do we have? We have a double bond oxygen with this hydrogen. We still have this OH. Great. We kicked out the alcohol. Good. And this is positive. Remember, Fischer esterification is alcohol plus carboxylic acid. And there's our alcohol. And then finally, how do we get the carboxylic acid? We do have a lot of water. That's typically the case when you have hydrolysis to push the reaction forward using Le Chatelier or Le Chatelier principle. And it's a long trek. Deprotonate that, and we have this. I did pose how many steps is Fischer esterification. Let me just label the products. So going in the reverse direction, which is to make the ester, you start out with a carboxylic acid, alcohol, and you start out with protonating, right? Protonating the carboxyl group. But my question was how many steps? 1, 2, 3, 4, 5. I'm a little surprised. I thought there would be 7. 6. Okay. Next is the amide. I'm going to try to fit the hydrolysis of an amide down here. What do we notice that's a little bit unusual is that we do get a charged product. You would have thought possibly that you formed just a neutral amine, but because we're under acidic conditions, your amine is protonated because amines are basic, more basic than alcohols. So we don't get the protonated alcohol as the final reaction product here, but we do get the protonated amine in this case. It is a pretty stable bond. This amide bond, some of you know this as a peptide bond if you know your biochemistry. We do use very concentrated acid, either HCl or H2SO4. When you do the mechanism, go ahead and, well, you could use HCl or you could use H3O+, because that will exist in a mixture of water and hydrochloric acid. I'm going to challenge you. I want you to try to do this mechanism. Pause the video, write out your mechanism and double check it. Correct your mistakes in a different colored pen, and that way you know what to look out for if you need to do this on an exam. Okay, before I get to the mechanism, just remember, because we form an amine it's basic and we're under acidic conditions, you will get the protonated amine, not the neutral amine. And again, we have our carboxylic acid, just like above. Okay, let's take a look at the mechanism. You know, the reverse of the Fischer esterification did take 6 steps. Let's see if hydrolysis of an amide are the same 6 steps. We did protonation first, right here. That sets us up for attack by water, and then we neutralize. So just like I mentioned here that we get the neutral tetrahedral intermediate after step 3, over here we get the neutral tetrahedral intermediate after step 3. 1, 2, and 3. Our job now is to get this to be a better leaving group by protonating it, then kicking it out. There's the kick out. And then this amine is basic, so it will be easily protonated. That's different than here, that alcohol is not as basic, So we're not using the alcohol to grab the H, we're using the water molecule. But here, the more basic amine is more basic than water. This will grab the proton and you have our final products. Again, the protonated amine and the carboxylic. Those are the 4 mechanisms to hydrolyze the 4 main carboxylic acid derivatives. But I have a treat for us. There's that 5th beetle, the forgotten carboxylic acid derivative. That is the nitrile. And here at the very bottom I have the nitrile, and that could be hydrolyzed as well. Where are you hydrolyzing the nitrile to get this carboxylic acid? Right? This carbon is that carbon. We've been drawing dotted lines across the bond we're breaking. We're breaking this bond. And that's perfectly fine to abbreviate the nitrile group or the cyano group as CN, but as you know, the nitrile has a C triple bond N, and that is what we're breaking. If you think about the mechanism, this is just as or even more stable than an amide, so we do have concentrated HCl and heat, but also remember how we protonated the this group to get it to finally leave? Well, that's just breaking one bond. We have to break 3 bonds here, so there is going to be quite a bit of proton transfers to eventually get this nitrogen to leave, and we also have to add 2 oxygens, right? All of these other cases, there was already an oxygen for the carboxylic acid. We just needed to add water to get the second one. Do you want to try this? Let me give you a hint, but maybe you don't need it. Very strong acid, concentrated. You're protonating first, and in a stepwise manner, you're trying to get this down to a double bond, then to a single bond, and then eventually breaking, like the amide did here. Go ahead and pause and give that a go, and when you come back, I'll show you my answer. Let's see what I did. We protonated the nitrile first to get this ready for attack. That's pretty common, but you know, in our previous examples we were protonating oxygen to make the carbonyl more easily attacked, but here we protonate the nitrogen. We get this triple bond to go down to a double bond, and now we're going to neutralize. And now we are at this point here. This looks like, if you look very carefully, this is the enol equivalent of an amide. I don't know if you see that, but the enol, remember, it's the double bond, and then we have a hydroxyl group. The keto form is if there's a double bond here and a single bond here. Anyway, we still got to reduce this double bond down to a single bond, so we're going to protonate again, and then we're going to use this lone pair to come in and to get this double bond to be a single bond. Look what we're getting. We're getting very close to a primary amide, because it is true, to make the nitrile, you typically go through a primary amide as a starting material. So now you see a bunch of whiteout, because I was very confident that I would neutralize this to get the neutral primary amide, but I just realized when I did that, well, I got to get another water molecule onto this carbon. So instead of deprotonating it, which I originally did, why don't I take advantage of this activated carbonyl and attack right away, again to get the tetrahedral intermediate. So it's the normal hydrolysis now of this protonated amide, just like we saw with the hydrolysis of the amide previously. Okay, so now it's a bunch of proton transfers to get this to be a good leaving group. We neutralize first, then protonate the amine, and then again, remember how we kicked out leaving groups? We use the lone pair. I call this the internal lone pair, or the lone pair within the molecule. And we get to the ammonia and this protonated carboxylic acid. Ammonia is basic, so it's going to easily grab that proton to get our final products.